Hi. Yeah, hello. Thank you so much, Martin, for that lovely introduction. And I'm really pleased to be here to talk to all of you about our changing relationship with the stars. So I'm going to start with a question. What if I told you that there is something so powerful that just looking at it, in fact, just looking at a photo of it, would make you more creative, more curious, happier, and less stressed, even weeks later, that would help you feel more connected to other people, more generous, less materialistic, that would help you feel as if you have more time? Well, that is exactly what psychologists have found for the stars. The starry sky is one of the most powerful sources that we know of the emotion of awe. That's the feeling that you get when you're confronted with something vast that dwarfs you, that's beyond your capacity to comprehend it. When psychologists want to trigger awe in studies, often they just show people the stars, and they've found that awe improves our well-being in the way that I've just mentioned, but also it changes our outlook on life in quite a profound way. After feeling awe, people make more ethical decisions. They're more likely to help others. They care less about money and more about the planet. So it seems that experiencing the sheer vastness of the cosmos for ourselves shifts our focus away from selfish daily concerns towards our connection to a bigger picture. And yet, just as we're realizing how important this view is, we're losing it. Every society through history all around the planet has been inspired by the heavens. Until now, with artificial light pollution, this connection with the universe that we're part of is fading. So instead of thousands of stars in the sky, in today's cities, we now see only a few dozen, even on a clear night. 80% of people in Europe and the US can't see the Milky Way at all. So through science, we've got this wonderful intellectual understanding of what the universe is and how it works. But what about our physical connection, our direct personal experience of the sky? So in the human cosmos, I look at what the sun, the moon, the planets have meant to people through history, how they shaped humanity and why they're important today. And the book itself is divided into 12 chapters. So each one looks at a particular moment in history, and explores a different way in which the stars have inspired civilization, especially Western civilization. And together they show how our view of the cosmos, the way we understand our universe, has been a major driving force in all aspects of human life. So the sky is not just a pretty view, that this quest to understand the heavens has been important for astronomy and science, of course, but also in religion, politics, art. And I'm particularly fascinated to how we live and how we see ourselves today. So tonight I'm going to pick out just some of those stories to talk about before coming back at the end to this idea of awe. So let's start at the beginning. How did our earliest ancestors see the world? So let's go right back to the Paleolithic era, and in particular to Lascaux Cave in France. And this is one of the most famous caves in terms of its art. Its walls and ceilings are covered in amazing pictures of animals, oryx bulls, horses, stags. They're 20,000 years old. So this is a glimpse into what was going on in the minds of some of our earliest ancestors. And one of the most intriguing paintings in the cave is this one. It's called Bull number 18. It's an oryx bull, the biggest bull that's painted in the cave. And above its shoulder is this strange pattern of 6 dots. And what's really interesting about these dots is that very similar patterns keep reappearing in in art, all around the planet. You've got the Lascaux dots on the bottom left here, and if you look at the 4 pictures on the right, the bottom 2 are sort of different appearances of these dots from Native American art. The middle top picture, that's from Siberia. That's a picture from a Siberian shaman's drum. The top right is the logo of the modern car manufacturer Subaru. And these 4 pictures are all representing the star cluster, the Pleiades. We've got the Pleiades on the top left there. And so those Lascaux dots, they're 20,000 years old, but they look just the same. So that's raised this question of, well, could these dots be representing the stars, the Pleiades? And what makes this even more interesting is their position in the cave, just at the shoulder of this bull, because that's exactly where the Pleiades appear in our modern constellation Taurus. And the whole sort of picture looks really similar. You've got these forwards facing horns defined by stars at their tips. There's the eye, which is the prominent star Aldebaran. The speckles on the face is the star cluster, the Hyades, and then you've got the Pleiades at the shoulder. So the question is, like, could they, instead of painting animals, were these artists at Lascaux really painting pictures of the stars? You know, could they have been the ones that came up with this association of the Pleiades with the bull in the first place? And could that constellation have survived until us today? And it's really hard to know, to prove what the artist meant by this picture, but there are several different lines of evidence that all suggest that this is at least possible. One of those is analysis of ancient myths. So there are various ancient myths, traditional stories that appear all around the world in sort of different versions in different places, but it's the same basic story. And one of those is called the cosmic hunt. The basic story is that an animal is hunted, it's chased up into the sky, and it becomes a constellation. And you see different versions of that story with different animals, different constellations involved, everywhere from ancient Greece to Africa to America. And researchers have compared the different versions of this myth, looked at the similarities and differences, come up with family trees to try and trace these stories back to their origin. And they concluded that the cosmic hunt story actually originated back in the Paleolithic. So that's some independent evidence that people at the time were telling stories about animals in the sky, and that those stories can possibly survive until us today. And another approach to understanding what kind of cosmology the people of the Paleolithic might have had is to study the beliefs of traditional hunter-gatherer communities. You have a surprisingly sophisticated understanding of astronomy. For example, the Chumash people, who lived until recently in California, they're thought to have led lives of similar complexity to the artists at Lascaux. They have a lot of cave art, which is filled with celestial symbols. And they too saw animals in the sky. For example, they saw the star Polaris as a sky coyote, which gambled with the sun each night over the fate of the people below. Something else that's really important to a lot of traditional communities is the rising and settings of star constellations. So when we look at the stars through the night, because of the rotation of the Earth, they seem to be circling through the sky. They're circling around the celestial poles, which are the points directly above the North and South Pole in the sky. And so stars that are close to the pole will always be visible, and others will rise and set through the night. And because of the Earth sort of traveling around the sun, stars will also become visible and disappear at different times of year. And it was these annual risings and settings that were very important to people. A lot of communities base their calendars around them. And in particular, the Pleiades feature a lot. So for the Maoris, for example, the rising of the Pleiades signals the new year. And people often relate them to seasons and events in the natural world. So in North Africa, the setting of the Pleiades heralded the coming of the hot, dry summer. Their rising signaled that the rainy season was about to come. And of relevance to bull number 18, for the Native American communities, such as the Blackfoot, they traditionally connected the visibility of the Pleiades to the life cycle of the bison, which they hunted. So different stages in the bison life cycle would be related to what the Pleiades was doing in the sky. When the Pleiades set, for example, it was time to hunt. So it's possible that the people of Lascaux had similar beliefs. One astronomer has calculated that when this bull was painted, the Pleiades would have, the rising and setting of the Pleiades would have marked the mating season of the aurochs, and suggested that if the artist had related the Pleiades to the life cycle of the aurochs bull in the same way that the Blackfoot people did with the bison, then it wouldn't have been a huge step to then link the Pleiades with a giant bull in the sky. One of the foremost experts on Lascaux's paintings, he was a guy called Norbert Augelas. He spent years studying them, and he didn't address this theory of star maps directly, but he did find that the horses, aurochs and stags in the cave were all painted at different times of year, and each species was shown during its mating season. So the paintings do seem to have, it was of central importance to people, and that they had a holistic view of the cosmos with the seasons from nature. So let's go briefly to Turkey in the 10th millennium BC. This is a site called Göbekli Tepe, and it's a series of stone circular enclosures, and they're built just at the transition between the Paleolithic era and the Neolithic. So this is 6,000 years before Stonehenge. And this site was built just before the crucial invention of farming, when people started to control and exploit the species that were around them. And it's in exactly the place where farming was about to arise. And so these circular enclosures, you can see there's benches around the edge. There are these T-shaped pillars, and two more giant pillars in the center. They were up to 5.5 meters high, and they seem to have been carved. You can see in the bottom right picture here, carved to represent some kind of anthropomorphic beings. They have belts, arms, loincloths, necklaces. One of them features this disc and crescent symbol you can see on the right, and it's been suggested that that represented the moon. And one theory about this site is that it was an observatory, that the pillars were for sighting stars in the sky. And that's unlikely, actually. The archaeologists excavating this site think that these enclosures were at least partly underground, and they quite possibly had roofs over. But it seems that they were still absolutely to do with how people saw their cosmos. There was an obsession with death here. The archaeologists have excavated the remains of lots of human skulls that were hung up for display inside these enclosures. To enter, they didn't have doors. You had to crawl through a small porthole, which was surrounded by carvings, things like animals on their backs. And the archaeologists working here think that these enclosures represented portals to the underworld, to the cosmic realm of the dead. And so this all represents an important change in humanity's relationship with their environment. In the caves of the Paleolithic, there are mainly paintings of animals. There are very few human figures. People saw themselves as part of nature. They didn't really distinguish between themselves and other species. But what's fascinating at Göbekli Tepe is that you still have the carvings of animals. You can see one on the pillar in the middle here. But it's the human figures that dominate. People were starting to see themselves as raised above nature. And you get this focus on the dead. There's a move from seeing animals in the sky to spirit worlds filled with human ancestors. And people are taking control of their environment, their cosmos. They're building their own portals to other realms. So it's this really interesting split away from nature, with people starting to control and manipulate their environment just before the birth of farming. So people talk about environmental factors that led to farming, maybe changes in the climate that led to increased pressure for food. But there's a growing idea that there also needed to be a shift in mindset. And what we seem to be seeing at Göbekli Tepe is this first really key shift in cosmology that changed people's relationship with nature. And that's what made farming possible, what made it conceivable, and so set the stage for all of the technological progress that was to follow and that has so defined our species. So next, we're going to jump forward to some of the first written records about human beliefs about the cosmos, and to the birth of an idea that's been really influential through human history, which is that our fate lies in the stars. And this is a story about how people's desire to predict their future in the sky, so very magical thinking, actually led to a crucial first step towards astronomy and science. And the evidence for this is held in the ancient library of an Assyrian king called Ashurbanipal. The library was discovered at his palace, which is near Mosul in Iraq in the 19th century. And it held thousands of clay tablets. Ashurbanipal ruled in the 7th century BC, but he collected texts from all over his empire, including Babylonian texts. Babylon was within his empire at the time, and some of them were centuries older. So altogether, this library gives an incredible insight into the beliefs of this ancient culture. And there are a lot of practical texts, things like tax records or bills, but above all, they reveal this absolute obsession with what was going on in the sky. So the Babylonians and the Assyrians, they still had this holistic view in which they saw events on Earth and in the sky as completely connected. And that was common in ancient civilizations, and it often made a lot of sense. So for the ancient Egyptians, for example, the star Sirius appeared each year just ahead of the flooding of the Nile, which was a hugely important event in their calendar. Their agriculture depended on it. For the Mayans, it was the appearance of the planet Venus, which heralded the coming of the rainy season. But the Babylonians, they really took this to extremes. They saw every event that happened in the sky, from the changing direction of the planets to lunar eclipses, as warnings from the gods of things that were about to happen on Earth. There's a compendium of thousands of omens that was found in the library, although it was compiled a long time before that, called Enuma Enlil. And it says, for example, if on the first day of Nisanu, that was a month name, the sunrise looks sprinkled with blood, grain will vanish in the country, there will be hardship, and human flesh will be eaten. Another one says that if a solar eclipse takes place while Jupiter and Venus are visible, the country will be attacked. Lunar eclipses were seen as particularly important events. They often foretold the death of a king, and the area of the disk that was darkened first, that would reveal the part of the known world, and therefore which king would be affected. And so knowing what was going to happen through these omens then enabled them to carry out rituals that would dispel the evil and stop these terrible things from happening. So, for example, if there was a lunar eclipse, the king would temporarily step aside from the throne, and somebody else put there instead, a beggar or a criminal, and then that person would be executed. So the omen had safely come true, the king had died, and then the real king could come back to his throne. So Ashurbanipal had a strong practical reason for collecting these texts. He needed them to stay ahead of these omens, to stay in power on his throne. And so he had teams of priests who watched the sky night after night, recorded what was happening. But the best at this was the Babylonians. They watched the sky nightly for centuries before and after Ashurbanipal's reign. This is an image of what Babylon might have looked like in around the 6th century BC. And you can see that tower right in the background. That's the Etemenanki, the gateway between heaven and earth, where the priests conducted their nightly observations of the sky. It's immortalized in the Bible as the Tower of Babylon. And over time, over the centuries, because they had these meticulous records, the priests started to see repeating patterns in the celestial motions, even in the wandering paths of the planets, which seemed quite erratic at first, or tiny variations in the speed of the moon and sun. And so they noticed repeating cycles, and they were able to develop mathematical models then to describe them. So at first, they identified great cycles. So periods of time after which certain types of events would repeat. Venus, for example, repeats its wandering path every 8 years. Jupiter every 71 years. The pattern of eclipses roughly repeats every 18 years. And then around 400 BC, the priests, they came up with an invention that made them even more powerful. And that was the zodiac. So as Earth moves around the sun during the year, that means that the sun for us in the sky, it appears to move in a circle around against the background stars. That circle is called the ecliptic. And the Babylonians, they had a number system that was based on 60. They divided circles into 360 degrees. So the Babylonian priests took the 360 degree circle of the ecliptic and they divided it into 12 segments of 30 degrees each, and they named each one after a nearby constellation. And that is the origins of the zodiac that we still have today. We don't have all of the same constellations that they had, but several of them were inherited by the Greeks, and we do still have those today, including the bull of heaven, Taurus. But the reason that the priests came up with this zodiac is because they wanted an accurate coordinate system in the sky, so that if they observed an event happening, a planet changing in direction or a lunar eclipse, they would be able to note down to the degree exactly where that event happened in the sky. So that made their observations much more precise. And shortly after that, they were able to come up with arithmetic methods to describe the repeating cycles that they'd identified. So they had complex mathematical rules, essentially, to compute the changing positions of different celestial bodies in the sky over time. And what this meant was that they could predict celestial events in advance. They didn't actually have to watch the sky at all. And that was a crucial moment in human history. The Babylonians, they were driven by this desire to read these omens in the sky. And because of that, what they ended up doing was they became the first people to use numbers, mathematics, to model the universe. They moved from an analog cosmos, if you like, to a digital one. And this approach allowed them not only to measure and observe celestial events, they were actually able to predict what would come in the future, maybe not in the way that they'd expected. And so what they were doing with their omens and their horoscopes, that ultimately led to what we now call astrology. But their mathematical models also enabled astronomy, a scientific approach for measuring and understanding the universe. That approach that's been so influential for how we live and how we understand everything in our environment today. So we started off with this holistic cosmos with earth and sky, humans and nature all entwined. I talked about that first split away from nature that heralded the birth of agriculture. And then we had the first use of maths, numbers, to make sense of the sky. So now let's look at how we invented our modern sense of time. And this story starts with a medieval book that's held in the Bodleian Library in Oxford. It's called MS Ashmole 1796. It was written in the 14th century, and it consists of around 200 pages of calf skin bound between leather-covered wooden boards. And as well as text in Latin, it includes several diagrams showing complicated mechanical arrangements of axles and wheels, and they're really sophisticated, unlike anything else that's known from this period. And an astronomy historian called John North, he translated this manuscript in the 1960s, and he realized that it was describing a spectacular invention that was created by a man called Richard of Wallingford, who was the abbot of St Albans from 1327 to 1336. And this is Richard. He had leprosy, in case you're wondering what's going on with his face. And he's pointing towards his invention. It's a huge celestial clock that was installed high on the wall of the abbey's church. And it was like nothing that had been seen before. It was far more than a clock. It was a sophisticated, self-moving model of the cosmos. Even 2 centuries later, a witness described it as a marvel still without equal in all of Europe. They said it showed the workings of the universe from the oceans. But north in the Bodleian Library, he realized that he was holding Wallingford's own instructions for building this very machine. And I want to say a bit about its story, because it's not just an impressive invention. It symbolizes a key transformation in human history, when we took time out of the cosmos. So what do I mean by took time out of the cosmos? Well, I've already talked about how for much of human history, time was bound up in the cycles of the sky. So days, months, seasons, years, are all defined by the movements of the sun, moon, and stars. And there are still people, for example, the Amandawa people of the Amazon, who think in this way. They don't count past 2 or 3. They don't have a separate word for or concept of time in itself. There's just events and changes that happen in the world. But we do think of time as a separate thing that passes, something you can count and measure regardless of what's going on in the sky. And attempts to count and measure time started very early in human history. The Babylonians, Egyptians, Greeks, they all used sundials during the day and star clocks at night to mark the passing of time. There were terrestrial methods as well. So sand timers, water clocks, burning candles. But these weren't accurate for long periods of time, and they'd need to be frequently reset in line with the sun and the stars. So ultimately, time came from the sky. And it was the monks of medieval Europe who became particularly obsessed with time. The way they showed devotion to God was through a strict daily schedule of work, study, and prayer. So other faiths at this time, Judaism, Islam, the Eastern Christian churches, the timing of their daily prayers depended on natural cues such as sunrise, noon, sunset. But Western Christianity, already by the 6th century, was starting to break away from this. In the monasteries, they introduced extra rounds of worship that were based on counting hours and all praying together at these precisely defined times. Increased the spiritual power of their worship. So they were really concerned with trying to find ways to measure the timing of their activities more accurately, especially at night. And we know that by the 10th or 11th century, they were using water-driven alarms that rang bells. There's a story about how a fire broke out in the Abbey of Bury St Edmunds in 1198, and when the monks needed water, they ran to the clock. But then from around 1283, a new kind of clock appeared in English churches. And it isn't described directly, but from financial records, we know that these clocks were expensive, made of iron, built by specialist craftsmen, often mounted high on church walls. So these were mechanical clockwork clocks. And this is the key invention that made those mechanical clocks possible and forever changed our view of time. It's called the escapement. And previous clocks, whether they were based on water, sand, burning candles, these are all different kinds of continuous flow. And that makes sense because time seems to pass continuously. But it's actually really hard to get those processes to run at a constant speed. And the monks were experimenting with mechanisms driven by falling weights. So you have a weight attached to a rope or chain that's then driving a train of gear wheels. But they were having the same problem. The weights would accelerate as they fell to the ground. And so the escapement, and the key bit is this sort of semicircular bit that you can see near the top there. It's an oscillating mechanism. It rocks backwards and forwards that regulates the fall of the weight into equal chunks. It's sort of alternately blocking and releasing the movement of that double gear wheel. So it's slicing up that flow of time into regular beats, the ticks of the clock, which can then be counted. And that was the key thing, changing time from a continuous flow into a series of equal countable chunks. Until that moment, the Islamic world and China had produced the world's most sophisticated water clocks. But from this point on, European clocks were the most accurate. And the very earliest description that we have of such a clock was in the book found by John North, describing Richard of Wallingford's clock. Now, Richard, he didn't invent the escapement himself. That happens several decades earlier, but his description of it is the very earliest one that we know. And what he does also seem to have been the first to do is to combine this technology with another tradition, which was of using geared mechanisms to model the cosmos. And this technology goes right back to ancient Greece and the Antikythera mechanism, which we heard about at the beginning in the 1st century BC. So this device, as you heard, was found on a shipwreck. You can see the largest sort of remaining part of it on the left there. And the X-ray in the middle is showing you that this is packed with gear wheels. It's made of clockwork, essentially. And then from the reconstruction, you can see this device was used to model the movement of the sun, the moon, the planets in the sky. And their movements were displayed using these pointers or hands that moved around this dial on the front of the device. And this was part of a centuries-long tradition. But all of these devices had a weakness, which was that you had to turn them by hand. And what Richard did with his clock was incredibly powerful, because using the escapement, he was then able to build a model of the cosmos that could run on its own, that could turn itself. So here are a couple of reconstructions of what his clock might have looked like. It had this big iron display dial, like six feet across, that was marked like with a map of the sky, and it turned in time with the circling stars. It had a bell that rang on the hour. It had a pointer showing the varying speed of the sun, a second pointer showing the moon with a rotating black and white ball that showed the phase of the moon. It also calculated eclipses. It showed the movements of the planets, and even the rise and fall of the tide at St Albans nearest port in London Bridge. And it took years and most of the Abbey's funds to build this. In the 1330s, towards the end of Richard's life, King Edward III visited the Abbey, and he scolded Richard for neglecting repairs to the church and spending all of his money on the clock. And Richard replied that future abbots could rebuild the monastery, but no one else after his death would be able to finish his clock. And he was right about the importance of this technology. The tradition of clocks soon swept through Europe, and it was these astronomical clocks like Richard's clock that did that. They started to appear in monasteries, but also in public squares, in towns, with these complex astronomical displays. So time was still seen as embedded in the wider universe. And this link with the cosmos gave the clocks divine authority. They were modeling God's creation, essentially, and this made them hugely powerful as they increasingly regulated people's lives. It was what made people so willing to submit to them. But ultimately, ironically, it was these same clocks that helped to weaken the church. So historians now see mechanical clocks as the crucial invention that drove economic development and lay the groundwork for secularization, capitalism, and the modern industrial age. So more accurate timekeeping, that allowed increasing regulation of work and workers, of course, but the clocks also changed how people thought about time and about the world. So just to give one very specific example, hour striking, these mechanical clocks had bells that struck the number of hours on the hour. And that meant that everyone within earshot became aware of time, not just as a series of passing events, sunrise, noon, sunset, but as something you could count, something that accumulates through the day. And these bells, they controlled people's lives. They set the timing for work shifts, market trading, opening hours at the pub. So they drove a more mathematical way of thinking in general. Many people wouldn't have been able to count before this. And now, just to conduct their daily lives, they had to be able to count at least to 12. Another difference was that the monastic daily schedule, previously imposed on everyone, used hours that varied in length with the season. So there were always 12 hours in a day, from sunrise to sunset and sunset to sunrise. But with mechanical clocks, there was a move to equal hours, the 24 hours in a day that were always the same length, regardless of what time of year it is. And so that cut ties with the church. People in the towns were now following this more secular timetable, but it also cut ties with the seasonal patterns of the sun. So time was becoming an abstract quantity, not directly linked with anything in the physical world. So now when we think about time, we really don't think about the rhythms of the cosmos, but about something much more like money, something we can count, spend, waste, buy, save. So over the next few centuries, clocks became more accurate, and it was really the astronomers, people like Galileo and Huygens, who were coming up with new designs for clocks. So like the Babylonians, they wanted to be able to make more and more accurate astronomical observations, and to do that, they needed ever more accurate timekeeping. But as clocks became more accurate, they dropped those astronomical displays. So clocks now, they're no longer copying the movements of the sun and moon. They exist in time as timekeepers in their own right. So time is no longer held in the cosmos, but in our machines. So let's talk about power. The beliefs that we have about how the universe works have always defined how we live on Earth in terms of setting political structures and deciding who gets to be in charge. Anthropologists think that as long ago as the Paleolithic, knowledge of celestial cycles was tightly guarded by the elites. It was this knowledge that gave them their power. And if you look at ancient civilizations, whether it's the Romans, Babylonians, Egyptians, Mayans, Chinese, for all of them, rulers were taking their authority from the heavens. So here we've got the Roman Emperor Claudius depicting himself as Jupiter. There's the 11th century BC Chinese Emperor Wu, who was known as the son of heaven. And here's the Egyptian pharaoh Akhenaten. He depicted himself as son of the sun. So all of them are modeling themselves on divine celestial beings. Sometimes they're taking credit for seasonal changes, such as the arrival of the rainy season, but they're all using the power of the cosmos to cement their status. It's very hard for people to question authority if that authority is being drawn from just how the universe works. And you might think, well, that's not really where we are now. You know, now we have a much more rational approach to things like politics. But actually, as ideas about the universe have changed, that has fed through into our political structures. So as soon as Copernicus put the sun at the center of the solar system, for example, immediately kings in Europe started modeling themselves on the sun with their subjects orbiting around them. On the right here, there's an image from the Palace of Versailles in France, showing King Louis XIV as the sun with his rays spreading out around him. But it was Isaac Newton, who triggered a much more fundamental change with his laws of motion and gravitation. So he revolutionized physics with this idea that you have universal mathematical laws that define the motion of everything in the cosmos, from particles to planets. So he was continuing to build this powerful mathematical model of the universe. And this meant that celestial bodies aren't divine beings that can do whatever they like. They have to obey the same rules as everything else in the universe. And that led to the idea that, well, if that's true for the universe, shouldn't that be true for people as well? Shouldn't everyone, from commoners to kings, have to obey the same laws? And these ideas were really influential during the Enlightenment and into the 18th century. And you can see that in the metaphors and the language that people were using. There's a lot of astronomical and mechanical imagery. So here we've got Lord Bolingbroke talking about the sort of increasing role of the English government as a check on the power of the king. And he said the monarch can move no longer in another orbit from his people. Or here's the French legal scholar Montesquieu, who's also talking about the English government. He says it is with this kind of government as with the system of the universe, in which there is a power that constantly repels all bodies from the center and a power of gravitation that attracts them to it. So people were very concerned about the balance of power, this balance between centrifugal and centripetal forces that Newton talked about as holding the planets stable in their orbits. And they wanted to replicate that in a political system. You didn't want to have too much gravitational pull dragging everything into the central sun. You'd end up with a draconian dictatorship. But on the other hand, if the ties became too loose, everything might hurtle away into anarchy and chaos. So people were really interested in how could you define governments to have this right balance of forces. And these ideas were really popular among revolutionaries as well in America and France. One of the most influential people calling for revolution in America was Thomas Paine. He wrote a pamphlet called Common Sense, which really tipped the balance of popular opinion in favor of revolution. And he used a lot of astronomical metaphors. For example, he said, "In no instance hath nature made the satellite larger than its primary planet." He means the sun there. And as England and America, with respect to each other, reverse the common order of nature, it is evident that they belong to different systems. So he's essentially using an argument from Newtonian physics about the relationship between a sun and its planet to argue that because America is larger than England, it should therefore be independent. And after the revolution as well, when the founders of the United States were discussing how they should set up their new democratic system, they were using still similar ideas. John Dickinson said that the states ought to be left to move freely in their proper orbits, while John Adams said the US Constitution should control those attractions and repulsions by which the balance of nature is preserved. So they all had different ideas about how tightly controlled the states should be by federal government, but they're all working now in this new Newtonian framework. So this was no longer about the divine right to rule. This is about a society having to follow logic and physical laws just as the cosmos does. And there's one more detail about this that I love, which is that before the revolution, America was seen as a colony or planet orbiting the central sun of England. But this raised a question, what would happen after independence when that central gravitational influence was removed? So once they formed the new democracy of the United States, they needed a new metaphor. They couldn't just be a planet drifting on its own without a sun. So they came up with the idea of a star constellation. In one newspaper at the time, a correspondent talked about the US as a constellation founded upon the principles of perfect equality, a republic amidst the stars. And so when they needed to come up with a new flag, there was only one way that they could represent the states, as a constellation of stars in the sky. And so those Newtonian ideas that the universe works as a mechanical system that's balanced and follows predictable laws, that's all come from astronomical observations, that vision is absolutely at the heart of the democracies that we live in now. So next I want to tell you a story about light. So most of our information about the wider universe comes from the light that reaches us here on Earth. For most of history, that's been pretty much our only source of information about it. So this is a story about how we've changed what we do with that light. So this is William and Mary Huggins. They are husband and wife astronomers, and they lived in the 19th century. And before he married Mary, William was a keen amateur astronomer. He set up this observatory in his back garden in Tulse Hill in London. It's just round the corner from where I am right now. And he used to look at the stars, draw sketches of the planets, but he was left feeling kind of dissatisfied by this. He wanted more from his astronomy. So one evening in 1862, he went to a lecture at London's Pharmaceutical Society, which is now the Royal Society of Chemistry. And this changed his life. The lecture was about work by the chemist Robert Bunsen, who was famous for inventing the Bunsen burner, and the physicist Gustav Kirchhoff in Germany. And they had invented a piece of equipment called the spectroscope, and they were using this to study chemical elements. So essentially, you probably know that different chemical elements, if you put them into a flame, that flame will burn with different colours. And Bunsen and Kirchhoff, rather than just sort of describing those different colours by eye, they were using a prism to split that coloured light into a spectrum so that they could then analyse the presence and absence of different frequency bands in the spectrum. So kind of moving from a qualitative to a quantitative approach. So in the diagram here, you can see the famous Bunsen burner that's labelled D, and there's a sample in the flame, and then that light goes through the telescope. It's split, but the light split by the prism that's labelled F, and the spectrum goes through the second telescope, and then they can analyse it. And using this method, they showed that different elements burn with different patterns of light. You can use the spectrum of light to identify different elements. And the lecture that Huggins went to, it mostly focused on using this to analyse chemical samples in the lab. Chemists were also using this technique to discover completely new elements. But it also mentioned that Bunsen and Kirchhoff had used their spectroscope to analyse sunlight, to probe what elements are present in the sun. And they'd shown that this distant celestial body was made of some of the same elements as we find on Earth. And that was an incredible result at the time. Previously, this is something that had been thought impossible to know. People thought that we could describe the appearance and the motion of distant celestial bodies, but not their chemical composition. And now here was a way to do it. And Huggins was captivated. He later wrote that hearing about the discovery was like coming upon a spring of water in a dry and thirsty land. And he realized that he could use this method to study the stars. He wrote, "I felt as if I had it now in my power to lift a veil which had never before been lifted, as if a key had been put into my hands which would unlock a door which had been regarded as forever closed to man, the veil and the door behind which lay the unknown mystery of the true nature of the heavenly bodies." And the lecturer that night, he was a chemist called Alan Miller, and he lived close to Huggins. And so they walked home together that night, and before they got there, Huggins had convinced Miller to collaborate with him. And so they kitted out Huggins's observatory like a chemistry lab with Bunsen burners, chemicals, batteries, vacuum tubes, and essentially they used a prism attached to the telescope to split starlight into spectra. And then they compared those spectra with the spectra that they got from burning different elements in flames in the lab. And it was incredibly difficult to do. If you can imagine how desperately weak the starlight is combined with, sort of compared to these bright flames that they were having to look at. If you imagine putting magnesium into a flame, for example. But they managed to show that although there's differences between different stars, these stars too are made of the same elements, the same building blocks of matter that we find on Earth. So the chemistry we have on Earth extends not just across the solar system, but across the universe. And after that, Huggins worked alone. He looked, for example, at different nebulae, these sort of diffuse kind of cloud-like objects in the sky, and he was able to distinguish different types. He showed that some of them are distant galaxies of stars, some of them are burning clouds of gas. And he was also the first to use the Doppler effect to study the motion of stars. So if a source is emitting light and it's moving towards or away from you, then the light that arrives, that you see, is shifted towards either the blue or red end of the spectra. So Huggins was the first to use these shifting in the spectra to estimate the motions of these stars relative to Earth. And so Then he met Mary, who was much younger than him. As a teenager, she'd read a magazine article about Huggins's work, and she was so inspired by it that she built her own spectroscope. That's the kind of teenager that she was. She was also skilled at the new technique of photography. And after they eventually married, they worked together, and Mary convinced William to use photography to photograph the star spectra. So they worked together. William did the developing, while Mary, she was younger and fitter, did most of the actual observing. And she found it difficult at times. She said, "Nobody knows how wearing science is. And it does take faith to be as happy in straining one's eyes to see little patches of light or of darkness as in feasting them on the beauties of the fields and skies and woods." But they did achieve really impressive results. They photographed hundreds of spectra from planets and different kinds of stars, and they published them in a grand atlas in 1899. And they included in that atlas a discussion based on their analysis of these different spectra of how stars might evolve as they burned fuel through their lives. And they speculated about how successive generations of stars might emerge from the exploded remains of the old. So it was an epic vision that hadn't really been seen before that point, of a dynamic, evolving universe, all from secrets hidden in the starlight. And that was the beginnings of the field of astrophysics. So now we have mind-bogglingly powerful telescopes that analyze not just visible light, but every part of the electromagnetic spectrum. And this field of study that the Hugginses helped to start has really shaken human culture. So now our myths about what celestial bodies are, where the universe comes from, they've been replaced with scientific, evidence-based stories. Aldebaran, the bull's flaming red eye, we now know is an aging red giant star that's forging carbon, oxygen and nitrogen inside it. Or Venus, the bright star of dawn and dusk that was the deity of love and of the rain. We now know it's an Earth-sized rock that's hiding volcanoes and mountains beneath its clouds. Spectroscopy has revealed that we really do come from the stars. Almost every atom in our bodies was once part of a star. And astrophysicists have used information from star spectra to pin down their life cycles. That's led to the discovery of completely new kinds of celestial objects, supernovae, black holes, neutron stars, and the Doppler shift in the spectra. That technique that was pioneered by Huggins, that's what first told astronomers that the galaxies are flying away from us, that the universe is expanding. And that led in turn to the theory of the Big Bang. So now we have a scientific creation story for the cosmos. So we hear a lot about the significance of Galileo when he first turned his telescope to the heavens, or about Newton and his mathematical laws. But I think that spectroscopy has been just as revolutionary, because it enabled us to go beyond just looking at the appearance and the motion of celestial bodies. Now we can understand what they're made of and how they work just by looking at the secrets that are hidden in the light. But there's an irony here, because although we understand more than ever about the universe, from a physical point of view, spectroscopy has contributed to our separation from it. No one actually looks through these telescopes. The photons are picked up by electronic detectors and analyzed by a computer. So again, there's a move here away from personal experience towards measurements and calculations. Our dominant source of knowledge and understanding about the universe is now our instruments, not our own eyes. And from a more practical point of view too, in terms of our everyday lives, our technology has pretty much replaced any direct personal connection with the stars. So we've got artificial light and heating, so that means we don't have to pay attention to cosmic cycles and how we live. We have clocks and GPS to tell us when and where we are. Our entertainment too comes largely from our screens. And for all the benefits of this technology, we're now realizing that this lack of direct engagement with our surroundings also has downsides. So neuroscientists are studying the effect on us of using sat-nav systems for navigation, for example. And it turns out that when we use sat-nav, we engage less with our surroundings and we prioritize information from the screen to such an extent that we ignore important signals from the real world. That's an effect that's led pilots to crash planes and GPS following tourists to drive into the sea. And over time, this also leads to structural changes in the brain as underused regions start to shrink. So just as sedentary lifestyles weaken us physically if we're not exercising and relying on our cars, for example, over-reliance on technologies to perform sensory or intellectual tasks like navigation, they seem to dull us mentally. Psychologists have warned that over time, this may even make us more prone to neurodegenerative conditions such as dementia. So the more we rely on computers instead of our direct experience, the more we erode our own awareness and skills. I've also talked a bit about time. Now we have breathtakingly accurate clocks that underlie so many aspects of our lives, but it also seems that the more precisely we measure time, the less of it we feel that we have. There's a phenomenon in psychology now called time famine, where people feel constantly rushed. Nearly half of Americans say that they lack enough time in daily life, despite all the modern conveniences we have and the fact that we're living longer than ever. And this matters. People often cite lack of time as a reason for not doing really important things. It stops them from engaging in leisure activities, from helping people, from visiting the doctor when they need to. Time famine has been linked to unhealthy eating, sleep problems, stress. So when we focus too much on counting minutes and seconds rather than enjoying the experiences that we have, that can damage both our physical and our mental health. Something else I haven't had time to take cycles when we're spending too much time in dim offices during the day, when we're looking at bright screens at night, that's leading to health problems from obesity, depression and insomnia to heart disease and cancer. When we block out natural cycles of light and dark, that's also devastating for other species, which also need the sun, moon and stars for timekeeping and navigation. A fifth of the world's land surface is now affected by light pollution, and that's disrupting bird and turtle migration, bat feeding, amphibian breeding, plant growth. It's killing trillions of insects. In 2018, scientists said that we should start seeing artificial light as a global threat on a par with climate change. So today we've got this wonderful scientific understanding. I've talked a bit about how we've built this powerful mathematical model of the universe and of physical reality, and it works incredibly well. It's exquisitely accurate at predicting the behavior of the physical world, and we've been able to use that to build sophisticated technology that's given us unprecedented convenience and freedom in how we live our lives. But looking back at this long history, at how we got here, what I'm trying to show in the book is that as we've focused on objective measurements and mathematical models in helping us to understand the universe, at every stage we've also sidelined our own experience. Now we rely on technology rather than our own awareness of our surroundings. We no longer see our own personal view of the stars as telling us anything useful or important. And I think that's why there's been so little outcry as our view of the stars literally fades away. And of course, this is a trend that mirrors our disconnection from nature more generally. So I want to finish by coming back to one more example of how our personal connection with the cosmos is important to this research on awe, which is exploring what happens to us when we see the stars. Chris Hadfield, the Canadian astronaut, he tells a story about his first spacewalk. He came out of the space station ready to prepare a robotic arm for use. He knew what he had to do. He was completely technically prepared. And then he saw the Earth. He said he was attacked by raw beauty. It was stupefying, he said. It stops your thought. He talked about the velvet bucket of stars going on forever in one direction, and then in the other direction is the Earth, this amazing kaleidoscope of colour pouring by as the planet turns beneath him. And he said it made him realise the power of the presence of the world as told to me by my ability to see it. And I think that's really beautiful, the importance of it not just being machines up there, but him seeing it. A lot of astronauts feel this. It's a phenomenon called the overview effect. So these hard-headed, technically trained people come back from space talking above all about the need to protect our planet and to treat each other better. And we get similar experiences when we look up at the stars from Earth as well, if only we get a chance to see them. A truly dark sky is something that I've experienced. At the beginning, psychologists have found that this makes us more curious, more creative, happier. But there's also a profound shift in perspective where people are more likely to help each other afterwards. They make more ethical decisions. They care more about the planet. Interestingly, people sign their names smaller after feeling awe, and they estimate their physical size as smaller. And neuroscientists have found that there's also a reduction in brain activity associated with the sense of self and also with language. Awe does literally stop your thought. And so scientists are building this idea that awe induces a kind of small self, that when we're confronted with something so vast, it puts our lives into perspective in a really important way. Our attention shifts away from our daily concerns that seemed so all-consuming before. We stop analysing details, and instead we see the big picture. And that changes us. It changes how we live and the decisions we make. Researchers talk about an awe deficit in modern society, which they think is making us more selfish and narcissistic. We're focused on our small screens all the time, and we're not feeling connected to the bigger picture. We're facing so many global challenges at the moment, including the climate crisis. And of course, we need science to help understand and solve those problems. But if we're going to make the changes that we need to make to live sustainably on this planet, then I think we're also going to need some awe. So just to conclude, we've now built on what the Babylonians started. We now have a sophisticated mathematical model of the universe. Our telescopes reach further into the cosmos than our senses ever could. But I think we need to rescue our personal experience of the universe. We talk a lot about the importance of our connection with nature for mental and physical well-being and for how we treat the Earth. And I think that we should include the stars in that, and that we should be fighting to keep our view of them. And that's first because of their importance for our cultural heritage. Our view of the stars is something that connects us with people around the planet and through history, but also because of their power to inspire and guide us today. Thank you.